The last tape that we want to develop on kinetics is the effects of temperature on rate. Well, remember that I told you that the rate of a reaction is being controlled by the collisions and also the mechanism, which are the steps in a chemical reaction. Well, temperature will have an effect on the frequency of collisions. If you increase the frequency, because the molecules are moving faster, bouncing off the walls of the container, and then therefore bouncing off each other, and what you're doing is you're giving them what they need, which is called the threshold energy. That's the energy to overcome the breaking of the bonds. So when you have a chemical reaction, there's a certain amount of energy they're going to need when they collide, and a certain velocity to overcome the breaking of the bonds. Let's take a look at a reaction that's pretty complex but pretty neat. Reaction that takes place in a light stick. We know light sticks ever since we were little children. Remember when you were a little child and you had a light stick and it was the end of the day and it was time to put the light stick away because it's time to go to sleep. Your mom used to tell you, give me the light stick, I'll put it in the refrigerator or the freezer, and then the next day your light stick would still glow but not go as bright. Well, that's directly related to the effects of temperature on collisions. When you cool down a reaction, you're basically slowing down the number of collisions and reducing the amount of threshold energy in order for the reaction to take place. So therefore there will be still reactant left the next day when you took the light stick out of the refrigerator. The chemical reactions in a light stick is actually pretty complex. There's two steps that take place in that reaction. The first step, this is for an example of a mechanism. The first step that has to occur is that there's hydrogen peroxide inside the stick. So in the light stick there are two compartments. The liquid that's on the outside of the light stick, and then there's a small capsule made of plastic capsule inside the light stick. And in one component you have your very complicated organic molecule that has this bond right here that's very unstable. This is called a phenyl oxalate ester. It has two ester functional groups. But what makes it unique is the ester functional groups are connected to each other, so this bond is very unstable. Then you have hydrogen peroxide, which is very easily creates free radicals, which also contains a bond that's very unstable. So at room temperature, these bonds can easily be broken. When these bonds break, you form this intermediate, this reaction intermediate. And a byproduct of the first mechanism step is this phenol. Then what happens, this reaction intermediate is loaded with potential energy. What happens, inside one of the compartments, usually the outer compartment, is a dye. And what happens is, since this is loaded with potential energy and it's trying to stabilize itself, when it stabilizes, it breaks down into carbon dioxide and gives the potential energy to the dye. The dye gets excited and its electrons jump to higher energy states. And what happens, it fluoresces. As the electrons come back down, they come back down a lot slower than they got excited. And the process of going down slower in steps creates a dye that emits visible light. So this is an example of an exothermic reaction. But this exothermic reaction is mostly light energy. Very little heat. There is some, but very little. So what happens is, in order for this reaction to occur, you're going to need energy from the room. But if you reduce the energy of the room, you'll slow down the energy needed to break these bonds. Therefore, you'll create less free radicals that can react with the ester to create the reaction intermediate. So by lowering down the temperature, you reduce the amount of reaction intermediate you need. that has to react with the dye to get it to glow. So that's an example of what we mean by temperature effects. And in this case, the effect is affecting the creation of the reaction intermediate. What's also interesting is that eventually what will happen in this reaction, all the dye that's present will be in an excited state and go through its own process of decay, which is a side reaction. And it's the decay reaction that we find that it's cool. This excited dye gradually breaks down and becomes the original dye molecule. But in that process, from the excited state to the ground state, that emission of light, which we call fluorescing, is what we enjoy about a light stick. But there's certain facts. The reaction is exothermic. Okay, and the question is, how quickly can we get the molecules the energy they need in order to create the intermediate? If the original reactants are at a certain temperature, remember that temperature represents average kinetic energy. So what happens is if we can increase the number of particles with energy to overcome the process of breaking the bonds, what will happen is by increasing the temperature, more molecules will have more kinetic energy, and therefore the reaction will go faster. So at temperature 1, the average kinetic energy would be here, but let's say the activation energy you need would have to be at this point, this amount of energy marked on this graph. This is a famous graph here called the Maxwell-Boltzmann energy distribution, where the area underneath the curve are the energy of the reactants. Okay, and the reactants right now at temperature 1, only the small portion of the reactants have enough energy to break their bonds. So the reaction is going to be really slow. But as you increase the temperature to temperature 2, now this whole portion of all the molecules on this side of the graph now have enough energy to break their bonds. So here is the set amount of energy that you needed to break the bond. So as increasing the temperature, you increase the number of molecules necessary as the reactants to break their bonds. Now there's an interesting fact. There's a famous equation called the Arrhenius equation. Initially it looks like this. Now if you're not into your logarithm math yet, savant Arrhenius came up with this equation that says all reactions have what we call a rate constant. And this rate constant is basically telling you how temperature will affect the speed of a chemical reaction. And it's equal to what we call a frequency factor. This would be the number of collisions that molecules would have to have in order for them to be able to break their bonds at, let's say, at minimum temperature of, I believe it's 0 Kelvin, in theory. And it's related to this mathematical function called Euler's number to the power of this relationship. And what do these things represent? Well, this E of A represents your activation energy. R represents the universal gas constant in joules, because we're working with energy. And T represents the temperature in Kelvin of your reaction. Well, this equation becomes quite powerful. If for some reason, now we can mathematically manipulate this equation to look like this. This is a derived Arrhenius equation, and in the old days on the AP, they would actually give you this equation. You don't really need to know the equation, but you need to know its relationship graphically. If you use a thing called calculus, what you can do is you can actually manipulate this equation to look like this. So we can take this, if we want to bring this down in math, you take the natural log of both sides of the equation, and you'd end up with an equation that looks like this, where so this exponential would actually come down. And what this is saying is if you plotted the natural log of your rate constant of your reaction at 1 over the different temperatures, so this is the temperature in Kelvin, you would get a plot that'd give you a straight line. And the slope of that line can help you get the activation energy of your reaction, because if you take the slope, okay, times a negative r, so if you take the slope of that line times negative 8.314, you can actually get the actual energy necessary for your reaction to take place, called the activation energy. So you can mathematically get the activation energy. So what you need to know is what plot could get you that, and what you would do with the slope of that line.